Hello, my name is Tim Camp. I'm Renewables Projects Director at London Offshore Consultants, and very pleased to be talking to you today about site-specific load calculations to support the development of offshore wind projects. And I'm also very pleased to be supporting the UK Offshore Wind Day 2021. I'm going to start by a quick introduction to Aqualis-Braemar LOC, but then move quickly on to talk about some of the drivers for site-specific load calculations. I'll talk first about offshore wind certification, the site conditions that are relevant and are typically measured prior to the design of wind turbine support structures. That'll lead me on to the needs for site-specific load calculations. I'll talk about the relevant standards for offshore wind turbine design and, importantly, the design of support structures, and then the kind of modelling that we need to perform in order to accurately calculate those loads. Finally, I'll say a word about an important topic for site-specific assessment, which is the possibility of tropical cyclones and seismic events. So first, just a brief word to introduce Aqualis-Braemar LOC. London Offshore Consultants merged with Aqualis-Braemar at the end of 2020, and we're very pleased then to form the Aqualis-Braemar LOC group. We are one of the leading independent companies in both offshore energy and marine consultancy. We have a very broad range of expertise covering marine engineering input and also loss adjusting to support these industries. We're an international partner. After Aqualis-Braemar and LOC came together, we now have 67 offices across 39 countries. In Korea, we have offices in Seoul and in Busan. We are very much involved in the energy transition, having been supporting offshore wind projects almost since the inception of the offshore wind industry. We're also active in modelling and supporting tidal energy projects, wave energy projects, and also solar PV, especially floating solar PV. So we have a broad range of services that span all of these industries, with a common factor being offshore. And as other companies are progressing to supporting renewables, it's our intention to generate 50% of our revenue from offshore wind and other low carbon activities by 2025. Our four main industries that we serve are renewables, particularly offshore wind, though as mentioned we're also involved in wave and tidal offshore, the maritime and shipping industries. We're also very much involved in oil and gas and other power industries as well. Around the world, we are just over 880 employees. As mentioned, we have offices in Korea, in Busan, and in Seoul. We have 67 global offices, and it's always our intention to try and serve clients locally, particularly where our services require third-party surveying or inspection services. And overall, we span 39 countries at present, but are always expanding. Our areas of work span these three main topics. Firstly, consulting and engineering. Secondly, risk management. And thirdly, the management of asset losses. Let me say a few words about these areas specifically in relation to offshore wind. So in offshore wind, we are often involved in supporting the project development process, often at a very early phase. So even at sort of wind farm concept design, we will be involved in assessing the suitability of ports, providing first estimates of energy yield assessment. We will be checking the suitability and availability of vessels to provide the construction and the O&M services. As the projects progress into perhaps front-end engineering design phases, we can provide the electrical engineering. We also provide geotechnical and geophysical engineers who can advise on the properties of the soil and the suitability for the wind turbine foundation. We often work for wind farm developers themselves in an owner's engineer role, where we typically provide package management services for components of the project, such as the wind turbine or the installation processes. As projects are bought and sold, so we support the transactions either in the design phase or even for operational projects with the technical due diligence, so we can advise on the value of an asset even prior to its construction. For contractors, we provide vessel design services, whether it's a new build service or conversion of an existing vessel. And that could be for all kinds of vessels, such as cable laying vessels, for example. We also provide wind turbine engineering specific services, so we can help choose the ideal turbine for a particular application, and also support the engineering around subsea cables, often a critical area for the wind farm. On the risk management side, I'll just highlight one of these services, and that's the marine warranty surveying. LOC is the premier provider of marine warranty surveying services during the construction and during the operation and maintenance activities for offshore wind. Just to explain a bit more what that is, really we are employed by the wind farm developer, but are the eyes and ears of the project underwriter or insurer. So in this role, we survey vessels to ensure they're suitable for the operations that they are planned to conduct. We approve documentation describing the operations to be performed offshore. And finally, we send surveyors to witness operations, all to ensure that the operations are carried out to best industry practice and at minimum risk. So the project developer benefits with the purchase of insurance for those operations. We're also one of very few companies who have been involved in the decommissioning of offshore wind turbines. Obviously, the offshore wind industry is still fairly young, so not many wind turbines have been decommissioned so far. But we've been involved in the decommissioning of turbines at 2 UK projects, at both Robin Rig and the Blythe offshore wind farm. Aqualis-Braemar LOC Group comprises a number of companies. I think the most relevant to the offshore wind industry is firstly our premier brand OWC, which is Offshore Wind Consultants, who offer project development services, owners engineering and technical due diligence for specifically the offshore wind industry. Innosea is our sister company in France, with particular expertise in wind turbine modelling. So that's the integrated load calculations to support the support structure design, but also with expertise in wave energy and tidal energy as well. LOC, as mentioned on the previous slide, is the premier provider of marine warranty services to the offshore wind industry. And finally, Longitude is our engineering house that provides a great deal of support to contractors, vessel owners, vessel designers, and we also act as designers for support structures for offshore wind. Let me now then sort of move on to the main topic, which is site-specific load calculations to support offshore wind energy. So, as you're probably aware, there are three main levels of certification which support wind energy projects, and these are equally applicable offshore and onshore. At the first level, there's the certification of main components inside the wind turbine machinery. That would be, for example, certifying the suitability of a blade, the wind turbine gearbox, for example. And a certifier would issue a component certification when that's been shown to be designed and manufactured to the correct standards. At the next level, there's the type certification, which really covers the wind turbine as a product. And for an offshore wind project here, we are more focused on the wind turbine rotor nacelle assembly, because that will be the generic product that is supplied to hopefully many wind farm projects. And that type certification, as we'll come on to, certifies the wind turbine machinery to generic classes of wind conditions. Thirdly is project certification, and this is specific to an individual project location, and it certifies the project based on the specific conditions, which include wind and wave conditions, water depth, for example, as we'll see later at the specific wind farm location. So these three sort of types of certification build one on the other to achieve the third stage of project certification. I described briefly the generic wind conditions that type class certification is conducted against, and this is an extract from the international IEC standard 61400-1, which specifies the wind classes and the turbulence classes that are defined by that standard. And these same definitions are shared by many other similar wind turbine design standards. So we can see that the wind speed classes are classes 1, 2, and 3, and these correspond to angle mean wind speeds of 10, 8.5, and 7.5 meters per second, respectively. They also correspond to a 50-year return 10-minute average wind speeds of 50, 42.5, and 37.5 meters per second. The standard also allows wind turbines to be type certified according to a tropical cyclone or typhoon class, and that corresponds to a slightly increased 50-year return 10-minute wind speed of 57 meters per second across each of those wind speed classes. The wind speed class also defines the turbulence intensity, and here there are 4 classes from A+, A, B, down to C, corresponding to turbulence intensity values of 18, 16, 14, and 12% respectively. Now that defines generic conditions for the wind classes, but obviously for an offshore wind turbines, the picture becomes much more complicated because there are more variables, particularly describing the sea state and soil conditions. So some examples here would be the actual on-site wind speed distribution, the extreme wind speeds, possibly including tropical cyclone events. There's the actual on-site turbulence intensity, which isn't going to be simply the ambient turbulence, but will also include wake effects. For offshore applications, the wind shear profile, the upflow angle, and air density are rather more consistent offshore than they are for onshore projects, and so don't show much variability. For the hydrodynamics, important parameters are the depth of water, the environment of the waves, often described as a scatter diagram of significant wave height as a function of peak period. The extreme wave heights, typically the 50-year return wave. The environment of currents at the wind farm site, both normal and extreme. And then soil conditions also vary, but in the soil type, the strength, and ultimately the stiffness that they provide to the wind turbine support structure. There's also the possibility, which is also very site specific, of seismic events, including soil liquefaction, which can obviously have a very detrimental impact on the turbine support structure. So why do we have to have these turbine site-specific load calculations? Well, as we've seen, the wind turbine can be certified according to the generic wind conditions as specified in the standards. However, the design of the wind turbine support structure is always site-specific, and that's because it would be impossible to provide generic definitions of all of those variables for a particular offshore wind farm location. So site-specific load calculations are therefore required for two reasons. Firstly, to verify the suitability of the wind turbine design for the actual conditions at the specified wind farm. And secondly, to provide the design loads necessary to design the wind turbine support structure. What are the relevant standards in this area? Well, I've provided some examples here from the IEC range of standards. I'm one of the conveners of Working Group 3, responsible for the design requirements for fixed offshore wind turbines. Part 1 of the IEC range, that's the 61400 series, provides the design requirements for the offshore wind turbines themselves. Part 1 provides design requirements for fixed offshore wind turbines, that's wind turbines fixed into the seabed. And Part 2, which is currently a technical specification, but which will soon become a full standard, provides design requirements for floating offshore wind turbines. These are the international standards from IEC, but there are quite a broad range of other standards and guidelines published by, for example, ABS, Class NK, DNVGL, Lloyd's Register, TÜV, UL, and other bodies. Some of the important contents of these design standards are the design load case specifications. These really specify the combination of design situations and the external conditions that the designer needs to take into account when either checking the suitability of the wind turbine machinery or calculating design loads for the wind turbine support structure. This is an example from the IEC standard where we can see some power production load cases. The design load case is defined by a design situation of the turbine, so that could include power production, as in this case it could include idling, it could include a fault state of the wind turbine, and it combines that design situation with a set of external conditions, which in each of these cases here include the wind conditions, the wave conditions, current, and the seawater level. So the design standards will specify quite a large number of these design load cases, covering both the normal operation or idling of the turbine, which define the fatigue loads that the turbine and support structure would experience, and the extreme situations that define the ultimate loads that the structure has to withstand. So after having then understood what the design load cases are, what do we then need to do to actually model them and calculate the structural loads? Well, offshore wind turbines are single structures subject to lots of different sources of applied loads. As we've seen, they are subject to aerodynamic loads acting principally on the turbine rotor, hydrodynamic loading, functional loads from the wind turbine itself, such as e-stops, and of course the gravitational loads acting on any offshore structure. And ideally, these would push us to an integrated model, which includes every aspect of the wind turbine structure and each of those sources of applied loading, plus of course the model of the wind turbine control system in one integrated tool. Also, wind turbines in their operation and the sources of applied loading are also very non-linear. Certainly the wind turbine control system brings a great deal of non-linear response to changes in the applied loads. The drag loads from the aerodynamics, the drag and the lift loads from the aerodynamic loads are both non-linear, as are the hydrodynamic drag loads on the support structure. And these requirements point us in the direction of time domain simulations to accurately capture those non-linearities. There are a number of pieces of software that provide all of these levels of functionality, including a FAST from NREL, the Flex 5 and Hawk 2 packages from DTU, SIMPAC, and DNV bladed software. Within LOC, we make use of both the FAST and bladed software packages. So where do these kind of load calculations appear in the project timeline? Well, they can support the project at multiple stages. At a very early concept design phase in the project, we would typically run a subset of all of the design load cases, possibly making use of generic turbine models if the actual numerical model of the turbine to be used in the project is perhaps not known at that very early project phase, or for other reasons is unavailable. And we can make use of these early calculations to screen different support structure concepts and therefore propose which is the most suitable and most cost-effective choice of support structure, considering monopiles, jackets, or possibly also different floating support structure concepts. At the feed level, we can make use of candidate actual turbine models to further define the support structures design loads, and also then to check the suitability of the proposed wind turbines to the particular site. In the detailed design stage, at this level, we would be performing full sets of design load calculations, each comprising several tens of thousands of individual simulations to define the fatigue and ultimate load envelopes as input to the support structure design process. And even for an operational project, you can make good use of numerical modeling, possibly, for example, as a component of a digital twin model of the offshore wind turbine to track fatigue damage as a function of the actual on-site wind and sea state characteristics. Let me say a few words finally about tropical cyclones. These aren't perhaps specific requirements of IEC 61400-1 because it's a phenomenon specific to certain geographical locations, but that certainly includes parts of South Korea. The approach adopted in the IC standard is to define the need to perform both a design level condition check and a robustness level check at different return periods of the external conditions. So the problem here is that twofold: is that there's perhaps greater variability associated with the tropical cyclone event, and therefore a possible change to the design rules and safety factors to ensure the same overall safety level, and that will impact, for example, DLC 6.1 and 6.2 of the design load cases. But also then for the extreme loading, the IEC standard follows the same robustness approach as the API standard. It assumes that a wind turbine structure has an exposure category of L2, which is for unmanned operation with medium consequence of failure, and specifies then the use of the 50-year return conditions to define the design level criteria. That's actually the same as for non-tropical cyclone wind conditions, but also specifies the 500-year return conditions to define the robustness level and the ultimate strength analysis to be performed during that stage. The IC standard defines two further DLCs for tropical cyclone prone regions. That's I.1 and I.2. Both of these are modeling parked operation, or that's either standing still or idling of the turbine rotor. And both of these define the robustness criteria. In I.1, we have a fully functioning wind turbine with the 500-year combination of wind and sea state. In I.2, we assume that there's been a loss of electrical network, which in some situations, with the lack of battery backup, for example, could influence the ability of the yaw system to operate properly. And in this case, the return condition, the conditions to be modelled are such that the probability of both the external conditions and the loss of the grid connection should have that 500-year return period. The standard also provides two annexes, H and I, which provide input for predicting extreme wave heights during cyclone events, and also provide the input for aligning safety levels in tropical cyclone regions. So please do see 61400-3-1 for some more information in this area. Some project references here for EDF and General Electric. LOC provided owner's engineer services for wind turbine and integrated load calculations for the Saint-Nazaire offshore wind farm between 2014 and 2019. We also typically performed these calculations on the floating wind farms, and one example of this here is the Groix and Belle-Île floating wind farm off France. This was a project for Naval Energies, which finished last year. Here the scope was to define the design loads for the combination of the wind turbine and the floating support structure, to define those load cases and then run a first set of integrated load calculations to assess the loads on the structure and on the turbine. Finally, we've also performed early stage site-specific load calculations to support GE on their North American projects. Here we've considered both gravity and monopile support structures, and the GE Haliade 12 megawatt and 13 megawatt turbines. So that hopefully gives you an introduction to the purpose and the features of site-specific load calculations to support the development of offshore wind projects. Do please feel free to email me at t.camp@loc-group.com if you have any questions, and I'll be more than happy to assist. At the end of the presentation slide deck, I've added an appendix which gives a full list of references to the LOC renewables work in site-specific load calculations. So thank you once again for this opportunity to speak to you, and I hope it's been some useful input. Thank you.